Okay, let's talk about Lab 4, which we've already done on Monday. So I'll just go through all the steps. The first thing, of course, you have to download the lab instruction, which is RLAB04.R over here, and credit.csv that goes with this particular lab. So download these two things. I've already done that, and I've created a folder called Lab04, and I've put this particular CSV file in there. So all I'll do is go to the properties, copy this particular address because I want to use it for setting my working directory in R. So my session is right over here, set WD, and I have to change the signs, something that we have done already a million times. Okay. Okay, so it's done. Let's look at the files that we have in the folder, cred.csv. So everything looks great. So the first thing that we have to do is we have to read this into a variable. So I'll create the variable credit, and I'll do read.csv, and I'll read this file, credit.csv. Okay, so I've already read credit data. Let's look at the structure of credit data. So this is a structure. There are 1,000 observations in there, or 1,000 rows in there. There are 17 variables. Now, out of these 17 variables, 16 are predictors because we are talking about decision tree over here. So our task is to predict something. Our task is to look at all the data and be in a position to say, okay, this person gonna default, do not give loan to this person, or this person is a good credit, give loan to this person or give more money to this person. So here 16 variables over here are the predictors, and the 17th variable, that is the target variable, default, whether this person has defaulted or not. And there are two levels for default, yes and no. So if defaulted, yes, otherwise no. So let's look at how many defaults are there. So we can do credit $default and table on that, and this will give us the information. There are 700 good credits, means did not default, and 300 bad credits, that implies it defaulted. Not only we can do that, we can also use something called prop.table and to do the same thing, table credit $default, and will give us the percentage or proportion. So here I got 70% no's and 30% yes. Similar kind of information, but prop gives you the proportions in your table. So that's another function you can have in your toolbox. Okay, let's go back to our session. So the first thing is that we have to download credit.csv. We have already done that. You can also open into Excel sheet, and then you can see how the data looks like. Once again, the 16 columns over here are the predictors, and the last column, which is the 17th column, is your target variable that you want to predict. Now, one thing that I talked about in the class is that when we are into classification, when we are into supervised learning method, we need two kind of data. The first one is the training data set through which we train our model. We tell the model, okay, these are the good cases, these are the good credits, and these are the bad credits. These are the characteristics of the good credit, these are the characteristics of the bad credit. So that is a training data set. And the second one is called the test data set, on which we test how good our model is, whether it's doing a fair job of classification between bad and good. So we have to cut our data into two pieces. How to do that? Two pieces, training and test. So how to do that? So for that, first of all, I'll create a random number between 1 to 1,000. And then out of those 1,000, I will select 900 random numbers. So how to do that? First of all, before I get into it, I have to do something that we have done in the previous example also, called set seed. And I set the seed to be 123. The reason why I'm doing this is because in the next step, I'll be creating random numbers in the range of 1 to 1,000. And as I repeat the same experiment, same algorithm again and again and again, I do not want to come up with different sets of random number, because then I cannot say whether I'm going in the right direction or not. I want my experiment, my development, my algorithm to be repeatable. So that's the reason I want to set the seed. So I set the seed to 1, 2, 3. Okay, now comes this next step where I generate numbers between random numbers between 1 to 1,000, and out of that I just want to take 900 random numbers. So these 900 random numbers, they represent the 900 random rows that I'll select from my data, which has in total 1000 rows. So once I do this, now train underscore sample has random 900 numbers which have been chosen from 1 to 1000 numbers. So let's see what is there in this train underscore sample. So these are 900 numbers in total, but they're random. So they could be like 900 something, say 190 over here, 166, 926 over here. So they're between 1 to 1000, they're total random 900 numbers. And now once I've done that, I want to choose rows that correspond to these positions. So 554th row, 629th row, 759th row out of my 1000 sample or data that I have. So that's what we are doing in the next step. So first I create the training data set. So for that, I create a variable called credit underscore train out of my credit data frame that I created in the first step by reading the data. Over here, I'll take all those rows that belong to this random 900 numbers ranging between 1 to 1000. And I need all the columns. So that's the reason there's nothing after comma. So that is my training data set. And for the test, I can do the same thing, but I'll put minus over here. That implies give me everything except these random numbers, 900 numbers over here. And instead of train, I'll make it test. Okay, so I created my training data set and test data set. So far so good. So one thing to be noted over here is the negative changes reverses the meaning. So here I'm saying give me the rows which are in training train underscore sample, but negative I say give me everything but these rows which are in train underscore sample. So that's what this negative sign means over here. Okay, let's go to the next step. So we are done with creating the test. We are done with creating the training. So let's look at the proportions of defaults in both the cases. So again, I use a function called prop.table, and it will create the proportions out of the table command. So let's look at that. So the proportions right now I have is 70-30. So that's very much like the proportions I previously had. So if I look at proportions, previously it was 70-30 in all the 1000 rows that I have. Here the 900 have the similar kind of proportion. So that implies my training data set is very much a reflection of the true data, the original data. Similarly, let's look the test data. What's the proportion in there? So if we do that, it's 67-33, but it's somewhat similar. So we are in good shape. So now let's run our decision tree algorithm. So first install a package called C50, which stands for C.5.0 algorithm. So we install this package. And then we have to call the library C50, something that we always do. So package has been installed. Let's call the library C50. And now all the functions are available. We can use them. So the first thing that we have to do is to run the simple command. This is the function C5.0. This calls the decision tree function. We pass on the credit data. One thing to be noted is that we do not need 17th column because 17th column is the target. So we put minus 17. That implies give me all the columns but the 17th column. So it will the credit underscore train minus 17 will have 16 columns with the exception of the 17th column. And then I have to specify which particular variable I'm targeting. So I'm targeting credit underscore train dollar default. So default is my target variable, and all the 16 variables on this side are my predictors. So with that, let me enter, and now the model is built. Okay, so now I can look at my model, how the model looks like. So the tree size is 57. There are 57 leaves in there, and the predictors are 16 and the number of samples are 900. So that is fine. And now I can look at the summary. So this is a summary of the model that I've created. So one thing that we see over here is something that I talked about in the class. A very good byproduct of decision tree is it gives you variable importance, which variables are important in deciding whether this person going to default or not. On the top is a checking balance. Checking balance, the most important variable when it comes to deciding whether this person will default or not. The second one is the credit history. The third one is the duration of the loan. The longer the duration, the more risky it is. The fourth one is saving balance and so on and so forth. So it gives us this information. The second thing is the confusion matrix. So here is classified as A and B, and here is the true classification of A. So these are all no's, but our algorithm for 35 times classify that as to be a yes. Here all the yeses are there, and our algorithm for 98 times classify those yeses to be 98. So if we take 98 plus 35, and so that's going to be about 134, you divide by 900, you will come up with this number 14.8%. So 14.8% is our classification error on the training data set. So this is all on the training data set. For almost 15% of the time, we cannot classify correctly. So that's our base error rate that we got on our training data set. Okay, so that is there, and along with that, we get the whole thing about the tree itself. So here we can see that okay, if checking balance is greater than 200 Deutschmark and or it's unknown, in that case the default is no. And it happens 412 times it's no and 50 times it's yes. So that's what it means. And similarly, the second one is if checking balance is less than 0 Deutschmark and between 1 to 200 Deutschmark, and credit history is perfect or very good, then yes is 59 times and 18 times no, and so on and so forth. You can read this entire decision tree, and in total is about 57 steps. So that is somewhat given over here when we did, so it's 57 is a tree size. Okay, so that is the summary of our decision tree that we created. Now let's go to prediction. So we have already created a model. Let's predict it. And for this, we use this function called predict. All it takes is, this is the model that we created in the previous step. And this is the test data set that we created. So let's enter this. And this gives us the prediction. So let's see how the prediction looks like. So prediction is no, 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 yes, yes, yes. It doesn't tell anything to us. And in total, there are 100 because there are 100 data points. If you remember, we created a test data set. So let's install another package that makes this analysis much, much easier. It's called generalized model and gmodel. So let's install this package. And so the package is installed. Let's load the libraries. Okay, so the library is loaded. And now we'll call a function called cross table out of this package. And this is a very useful function because it produces a nice cross tab that we can leverage. So the thing that it's doing in this function, it's cross table is a function. It's saying, okay, which particular thing that you're targeting. So we're targeting default out of our credit data set, credit test data set. And our prediction data frame is credit underscore predict. And we do not want any chi-square statistics, so I put that to be a false. I do not need proportions of column, proportions of rows, so I put those to be false. And I put some names to my dimension to be actual default and predicted default. Again, actual default gonna be the rows, and predicted default is going to be the column, RC. Remember that convention. So with that, this is the output that I get. So these are the actual defaults and these are the predicted defaults. So again, I get, so actual default was no and predicted default was no 59 times out of total 67. 8 times it was yes. So that is an error. Yes was yes 14 of the time, so 14 times was correct. 19 times was off, so 19 plus 8, that is 27. So our error rate on our test is about 27%. So in training it was about 15%. In reality, when it looks at the data which it hasn't seen, it produces error at 27%. Okay, so that is done. Now, how can I improve the model? And for that, we'll use the idea of boosting. So, so here's a function of boosting. Again, C5.0 remains the same. The only difference is I add one more parameter called trials. So what that implies is it will create 10 decision trees. So first it will create one decision tree. It'll look at the errors that that decision tree produces. And in order to resolve those errors, it will create another decision tree which will work on that error. And then again, some errors will be there. So third decision tree will be created to work on those errors. And again, some errors will be there. So fifth decision tree and sixth decision tree will be created. And in total, they're going to be 10 decision trees. So let's do this. And now we have created one more model called credit underscore boost 10. So we are using the boosting algorithm that we talked about in the class. Again, let's look at the model, how the model looks like. So again, the average tree size out of 10 is 47.5. The number of samples are, of course, 900. The predictors are 16, and the number of boosting iterations were 10. Okay, so far so good. Let's look at the summary the way we saw the summary of the previous algorithm. And so again, we get a variable importance chart. Again, checking balance is one of the most important one. In this case, the second most important is purpose. If you remember the previous time we ran it, I think it was credit history. And the year of residence comes second, third, and then employment duration fourth. Credit history is not fifth. So that is there. Again, we got our classification errors. So 4 over here and 30 over here are misclassified. So 30 plus 4, that is 34, divided by 900. So that comes out to be so much lower, about 3% error rate as compared to say 15% as we saw in the previous time. But once again, this error rate is on the training data set. Let's see how it does on the data set it hasn't seen, which is that test data set. And once again, you can see the decision trees that it has created, and they're like 10 decision trees in there. Okay, so we'll do the same thing. We'll test our model against the test data set that we have. The command remains the same, predict, and then the model and our test data set. You hit enter, and now everything is in there. And let's see how it does in our cross tab. So again, syntax remains the same. This is the target variable. This is the prediction that we just calculated in the previous step, and we put all other stuff to be false so that we get a clean picture. And hit enter, and we'll produce a cross tab. Okay, here our error rate is 13 plus 5, so that's 18. So only 18% versus 27% as we had in the previous case. So just with the change of the technique, now we have gone down from 27% to about 18%. So that's a almost 9% decrease, or I should say improvement in our accuracy. Okay, so that is great. Now, one more thing that I can do is I can make some of the mistakes to be more expensive than other mistakes. If you look at this matrix, if I say the actual default is no, and if I say yes, this person will default, that is not that bad a deal. However, actual default is yes, and I say no 13 times. That's much worse a mistake, because if you land $1 million to a person who's not supposed to get it, those $1 million are gone. However, if there's a person supposed to get $1 million, you say no. At best, you lose is the interest payments that person would be making. So the loss over here is far little as compared to loss over here. Loss over here is far greater than the loss over here. So for these kind of mistakes, we want to give a higher penalty versus on these kind of mistakes. Can we do that in a model? The answer is yes, we can do that. And let's see how to do that. So the first thing that we do is we create a list which will have all the names for a matrix that we will create. And this matrix is called error cost matrix. And this will have cost for or penalty for different kind of mistakes that the model makes. So the first thing that we do is we create a list. And this list has two elements in there. The first element is no, yes, no, yes. So as pretty evident over here, this first one is for the column and second one is for the row. So you got 2 rows and 2 columns. Rows have no and yes, columns have values no and yes. So far so good. Let's give some name to these elements, and this is the way to do that. We give the name to these elements, and now if you look at matrix underscore dimensions, you got 2 elements, predicted and actual, and they have value no and yes, no and yes. So far so good. Now let's create our cost matrix. So if you recall the first and the second lab that we did, we had some syntax on matrices, and this is syntax where you call matrix. And as I said in the first class and second class, matrix is nothing but a vector which has few more parameters in there. So this is a vector that has all the values which will go into the matrix. So 0, 1, 4, and 0. The number of this matrix is going to be 2. So that implies in total they're going to be 4 columns. So two columns, so 4 values. So two rows and 2 columns. And the name of the dimensions we will get from the list that we created in the previous step. So it's going to be no, yes, no, yes. And let's call it to be error cost. So let's hit enter. And if you look at this error cost, this is how it looks like. So we got actual over here, no, yes, no, yes. So this is if it's no and you predict that to be, the actual is no and you predict that to be no, then no penalty. If it's no and you predict that to be yes, then you predict it to be no and actual is yes, then it's going to be 4. And similarly, if you predict that to be yes and the actual is no, it's a mistake, but it's not that bad a mistake. If it's yes and and actual is also yes, then it's 0. So once again, you predict it to be no, the actual is yes, that's a huge crime. So let's put a penalty like 4 times more penalty than this error where you predicted yes, this guy gonna default and the actual was no. Okay, so now with that, all we have to do is to run the same algorithm that we had previously, and we just put one more parameter called cost, and we supply this error underscore cost to it. So this matrix will have all the cost that will apply on our model. And let's hit enter. Okay, so our model is built, and we can again do the prediction on our model. The same syntax that we had previously. Predict is a function. This is the model that we created, and this is the test data set. And we hit enter. Now prediction has been done. Now let's call cross tabulation, and let's see how a cross tabulation looks like, how our model is doing. So now if you look at this yes, actual is yes, and we predicted no. So we predicted no and this person actually defaulted. Those are 7 versus, say for example, with boosting it was 13, and with our previous model I think it was 19 or something like that. I think that is gone, but it was I think 19. So now this particular error is reduced to 7 instead of 13. Even with boosting it was 13. So now with ordinary decision tree, one tree, it's 7. However, this error has ballooned. It is now 30 versus 5 over here. But this error is not that bad an error because the actual default is no and we predicted yes. So that is fine. That is not a costly error and we can allow that to balloon. However, this error is so much smaller, and that's how we want our model to be. This is not a costly mistake, but having 13 over here is a very costly mistake. So this is another way in which you can improve the efficiency of your model and performance of your model. So let's do one last thing, and that is to do a very simple random forest algorithm here as well. So we'll install the package called random forest. Okay, so the package is installed. Let's do the library command, and let's call the libraries of random forest. Now all the functions hereafter are available to be used. And again, for random forest, the syntax is very similar to what we have done previously. One thing to be noted over here is that I made a mistake in the lab documentation. It has to be minus 17 over here because the target shouldn't be there in the training data set. So all I'm saying is this is my training data set and this is my target. And or in other words, these are my predictors in my training data set and this is my target. So that's the reason I put minus 17 over there, something that I've also done with the decision tree. And I hit enter, and now RF is my model. And I can do the same thing that I did previously. I can look at this model RF, there are yes and no's in there. So in total, um, no and yes, 158 over here, 52 over here. 158 plus 52 divided by 900, that'll give you the error rate. Okay, so that is my error rate. Let me look at the prediction. So again, I use the same thing. This is my model, and this is the test data frame. And now this has all the predictions in there. Again, I will use a cross tabulation to see how well my model is doing. And so this is how well my model is doing. Yes and no, I predicted to be no, and person really defaulted. That was 19. And actual was no, I predicted yes. That those are 5. So that implies, you know, there's a total of 24% error rate. But one thing to be noted is that these 19s are very expensive mistakes. So it seems like if we go with our error matrix method, then we can reduce this particular rate tremendously. It could be 7 over here, and then we can use some other functions or some other algorithms to predict these where we are wrong over here. But the point is, you can use different algorithms and choose which one is working for you based on how well your algorithm is doing in the test data set. So that finishes lab 4. And in the next class, we'll talk about how to improve model performance, how to evaluate model performance, and few more algorithms. Thank you.